I will start record this webinar and then share the screen.
Okay. It's time to start.
Okay. I think it's it's 8 o'clock p.m. in Beijing and Beijing time, and I think we can start our webinar today. Hi everyone, I'm Zhikang Yuan, the Chinese representative of IEEE DEIS YP. It's time for our monthly webinar again. This time, it's our great honor to invite Professor Yewen Zhang from Tongji University to share his work. At first, let me introduce Professor Zhang. Professor Zhang is a senior space strategy researcher. He was born in Zhejiang, China in 1955. He received a bachelor's degree, master's degree, and a PhD degree in electrical engineering from Xi'an Jiaotong University. He then joined the PCI in France as a postdoc research fellow, subsequently being appointed research fellow in 1996, he moved to the Department of Applied Physics, Hong Kong Polytechnic University as research fellow, and then joined the Department of Physics, Tongji University, as a full professor in 1997. After 2012, he is a full professor with Department of Electrical Engineering, Tongji University. He is the leader for 2 IEEE international standards. His research interests lies mainly in the field of space charge in dielectrics. Recently, he is also working on photonic crystals and metal materials for microwave application. His topic today is research on space charge in solid insulating dielectrics, long history, current situation, and the near future. Okay, during the webinar, if you have any question, you can type them in the chat box, and we will have about 10 minutes for Q&A. Okay, let's welcome Professor Zhang. I will stop sharing.
Okay.
You can share your screen.
Yeah, okay. But I don't know how to do it. Could you see my screen? No?
No, it's behind
yeah, okay.
The button you open your video.
Yeah.
Okay, we can see it.
Yeah. I try in this one. Okay. Okay, we can start.
Yes, we can start, of course.
Okay. Good morning, good afternoon, and good evening, good night. I'm in China, Shanghai, so now is in night 8 o'clock. I will present my research history for space charges. This is a long time because our domain is not very quickly. So over 30 years, I work on the space charge research. So very quickly schedule for the space charge history in dielectrics. The space charge effector maybe has a very early problem before electrical mechanism. Before a few thousand years ago, by the Thales and Plato, who names various names we call the scientist. So the history is like our scientific research. In the 17th century, Jeppert found the same electrostatics phenomenon. In 1933, Dufay proposed two fluid theoreticals called, sorry, I moved this one, called the mystery fluid. So in this year, we don't understand very well for electricity. The way to store this mystery fluid is used to the laden bottom. Now we know the bottom is a capacitor. In the beginning of the 20th century, electrics becomes the word, the correspondent, sorry, is a mistake. For the word magnetic, he can store the charge. At the beginning of the sentence of the last sentence, the polymer begins very fired used, so space charge effect is more important in this age. And so some relative capacity concept about the space charge. Space charge definition for space charge by IEC is not very scientifically, but we can understand what is space charge. Space charge is the net charge inside an insulating dielectric material, but the interface is very similar. It's also the night layer of the charge between the two different material, either two different insulator or the conductor and the insulator. So it's also called interface charge. Scientifically, electrostatics, electrics, space charge, interface charge, surface charge, etc. All of them are very close relation. So I present some effect of space charge in dielectrics. I can close this one maybe. Yeah, good. In dielectrics, for the electrical insulation, space charge in insulator can affect and modify the electrical field distribution seriously. It's clear and very easy to understand. And another phenomenon is not so easy to understand. The quick movement of space charge, for example, in jumping in the trip. So space charge may be induced the damage of dielectrical insulation. For the dielectrical functional material, for example, electrics or microphone is very useful. The space charge is physical basic of the electrics. But the effect of space charge for the dielectrics is also not very clear up to now, except for the modification to the electrical field. The others is need research, more research is necessary. So I present some methods for the measurement of the space charge, for space charge distribution in the solid dielectrics. Now in the application, after long time research, of course, since the 1990 years. So many research on the work for the measurement of space charge distribution. Up to now, there are 2-point methods. Why I call the 2-point now? We can see after this slide. For the measuring space charge distribution in the solid dielectrics in real industry and applications. One is the PWP method, the partial wave propagation method. And second one is the PEA method, the pulsed electrical acoustic method. And also the 0.5-point method, the TP, the SEMO plus method. But this one is not very wide useful in the practice. So PEA method and the PEA method, both an acoustic method, is like invest physical proceeding, so we can show the detail after that. The TP method is a thermal method, but is less apparent. So I present one by one. The principle of the partial wave propagation called the PWP method. The PWP method is also called LEAP. It means a laser-induced partial pulse method. It's the main way of a PWP method. Another way is a piezoelectrical induced PWP method. It's called piezo PWP. In principle, it's very similar. When the elastatics wave propagates at the speed of the sound in a dielectric, will destroy the balance between the original elastic force inside of the dielectric and their electrical force. So he generated by the charge, the small displacement, the move a little bit of the charge in the dielectrics. The very small displacement of charge, the move later, it reduces the change of the induced charge on the electrode on the dielectric two side. The charge of current or voltage can be observed by the external circuit. Thus, the obtaining information about the space charge distribution in the dielectrics can get. The spatial position corresponds to the time coordinate swing through the acoustic velocity. So from the space and the time, it can advance by the acoustic velocity. So the physical model, for example, this one is the original space charge distribution, and the wave propagation in the dielectrics. He can reduce the current outside. He move little bit. This one little bit move, so he gets a signal like that. This one is a corresponding the first interface charge. This one is a second electrical charge. This one very similar the interface the space charge inside. So potential between the two electrodes, there's a potential is like integral of the electrical field. The Poisson equation between the action, before the action of acoustic wave is very clear, and after during, not after, after the action of the acoustic wave inside the dielectrics, the Poisson's equation can write something like that one, but this one not very easy to understand. But after that, we can devise. There is a two part of action from the partial pulse. One is deformer of the sample. For example, the partial so charge the sample with deformer. So he can get the increment of charge density. And another one is move the displacement. One is deformer, another one is move. So deformer and the move. So the move, he reduce the increment of charge density, something like that. Compare this model, we can get the measuring for measuring unit with the high impedance. It means that we measure we're measuring voltage and the current outside. For measuring the voltage with the high impedance input amplifier and measure current for using the low impedance amplifier, we can get the current and voltage. For the one dimension, this one is not very easy to get the result of the E. We know this one, we maybe know this one, so we need to get the E inside of this one. For the former, in one dimension, there are the very simple relationship. U is the deformation, P is the partial propagation with time and position, and Y is the Young's model. So we can get the delta V outside by the measurement of the voltage and the current with a low impedance input. So this one, we can measure this one. We maybe know this one and this one, and we can get the electrical distribution inside of the sample. But for the very narrow, if the partial pulse is very narrow, with the tau, the partial waves, and the partial zero, so we can get. Could you hear me? The program? No.
Okay, it's okay.
Okay, we have attention. We can get current. Current is properly the low inside of the insulator. So this one is C0 is the original capacitor. P0 is partial. Chi is compositivity is like the of one of Young model, and V is velocity of the acoustic. So we can get the rho from the measurement current. Therefore, the measurement short circuit current is roughly proportional to the space charge distribution, and the time is proportional to the position of the partial pulse front. If measuring in open circuit, it will proportion to the electrical field. So if we measure current voltage. This one is changed to the electrical field. So in the if the without space charge, in the absence of space charge and without any application voltage, so the field like this one, the current signal in the vicinity of the electrical, in this one in here, vicinity of the electrical electrode is proportional to the partial profile of the partial wave. So we can get the clear partial wave like this one and this like this one. The which is the regarded of the shape of the partial pulse. So ITB, B is this one here, and ITA is another side. I don't note it. Is a partial is a propose the partial. So requirement and the generation. Now the problem is we can get the how to get the P, the partial wave. During the propagation with a special specimen, the in the age of 1990, over 10 years, the many research group try to how to get the suitable partial propagation. The firstly using the discharge, also using discharge, and using the quartz, and using the shortwave tube. After many tests, we found the research found that for using the laser is a very good one, but laser is very expensive at this age. So someone tried to using the piezo also already. That during the propagation, no, in principle, during the propagation with the specimen, the deform is very narrow partial wave can just very serious. So it requires the pulse not too narrow and unity seek the not unity to seek the high resolution. If the very narrow resolution of high, but the deform is very quickly. And the amplitude of the pressure is directly to realize the measurement sensibility. So it also needs the amplitude of the pressure base. Now we know about 1 megapascal maybe is suitable. Historical, there's many kind I just see. So there is many different name. So so we can find a very large list, the different name with a different method for the generation of pressure. Now, this the basic. We know the basic is same. So-called PWP method is a good one. For the polymer dielectrics, the dissipation of partial pulse propagation is more sensitive, but the attenuation is not sensitivical and can be ignored. The proposed standard used this important physical basic for the data processing. Required of the generation as also. Now is a two applied method, plus the laser generation, the pulse partial and the piezoelectrical induced pulse. For the laser general pulse, the sometimes also called the LIPP. The PRP, piezo electrical partial wave propagation method, generally by the piezoelectrical induced probe or generator. The resulting the partial propagation is similar to laser, about 1 megapascal. But the measurement resolution is not so good as the laser. So it's need to pay more attention to the problem of pressure coupling, because the laser is independent, but the piezo generator or probe is connected, so it's very important in the coupling in the interface for the generator and the sample. So this sample for the laser. Here is laser, is our lab. Is laser. Here is chamber. So there is chamber, the recorder, amplifier, and oscilloscope. So another advanced is for the coaxial sample, like a cable, PWP physical model needs to modify. The propagation is not uniform. He's like the focus. The the partial propagation from the outside to inside is induced the convergence of the pressure. So here is like this one. The cable, the problem is thick. The cable insulation usually is thick, the some 10 millimeter, 20 millimeter. Now someone is over 20 millimeter, so it's very thick for the measurement. So the effect is the relay this one is a focus like this. Is the propagation will ground, so it's also need to take in code. So the spot laser cannot too small. For the planar sample, this is not a problem because planar sample is usually 1 millimeter or over 2 millimeter, not very thick. So the spot of the laser usually very big. This one. For measurement current, something like this one, you see, if even without any space charge, this one, but E is not 0. E is also a function of the radial. So the current is also the relation with the field, convergence field. So this one, for the typical cable sample, insulation thickness 10 millimeter with a 60 kilowatt. The measured signal without space charge. So you can find the second one is bigger than first one. This one is the focus of the pressure. The measurement current with applied voltage without a space charge, something like this one. So you can find the ratio of the P in the outside of the inside. So the ratio of the two peak or arrow is proportion is over 3/2 times. So, but for planar sample, this ratio is equal 1. So then we quickly we have passed quickly for the PDRP method. And now we can propose the principle of a pulsed electrical acoustic method. For the acoustic method, a pulsed acoustic method is applied pulsed electrical field. Has produced a small dispersion. It's also dispersion, but this dispersion is reduced by the electrical field. For PDRP is reduced by the acoustic. So electrical field applied voltage, the change here move a little bit. So he interact the electrical field inside of the dielectric, induced the acoustic propagation on both sides. The charge move little. So one direction, another for another direction. So the acoustic signal can obtained for the measurement. From the measurement as an analyzer for the space charge distribution inside of the dielectrics. So this one is electrical reduced acoustic. We measurement acoustic, but measurement acoustic is not very easy. It also needs the electricity. So means the electrical change to the acoustic change to the electrical again. So we can measurement the electricity. Initially, is only used measuring the electrode at the electrode surface. It's need to take the remove the extend the reflection acoustic as well as the strong interference synchronicity with the applied voltage, because this one, if the applied voltage this plus is reduced very strong noise, so is sometime so synchronicity. So it's very important to separate this one. The first experiment, PEA, is completed by the Takada, but he don't know Takada with the MIT in Japan. But his experiment was in MIT in United States in 1983. So both laboratory claim to have the first proposal of a PEA method. However, the generally acknowledgement the Takada of Japan invited the PEA method. So the principle is like that. We're using the same, very similar electrical space charge distribution like the last presentation. So we applied the voltage in for the sample. He gets the acoustic this side. So we can get the this one, the acoustic measuring by voltage. So we can get in this side, the propagation move this side. We absorb from this side. He moved two sides, so we only measure the one side, the acoustic. So you can find the acoustic waves are very similar than the PWP method. So it's force electrical orange one. Force electrical equal to the electrostatic force dielectrics. Then applied when the applied pulse electrical field, this one is not equal to the two phase between two phase. So he gets the more measuring of electrical force of electricity dielectrics. So we measurement the variation of the electrostatic force by the transducer. In physical nature, PWP method and the PEM method are the inverse process of each other. So therefore, they are all the acoustic method. His resolution and his relationship between the position and the time is also similar the acoustic. So for the planar sample, this one applied here is applied voltage, high voltage. There is applied the plus voltage. So we can get the propagation, the acoustic here. We measuring acoustic with if we measuring with the high impedance input amplifier, we can measure the V, the voltage, but not current. So we can get a V. PVDF is proposed with the law, so it's easy. The evolution of the electrical force is proposed to space charge distribution, but the electrical signal obtained from the sensor measurement is not exactly proposed to the charge distribution. The sensor is not cannot get the directory force. So it's so usually the measurement of the result PA needs the less induced for the need to the proposed computationally. So it's called the signal correction or called signal calibration. There give note the at the high input impedance voltage amplifier, this one is usually here, but wideband is with a high impedance input voltage is not very easy to find and also very expensive. So now many research using the low impedance. It means the measurement not voltage but current. So this one we measurement the voltage. We get the signal is very similar than PWP. So high input impedance voltage amplifier is used here to average the signal many times to improve the signal to noise ratio. So it's possible to get the intuitive space charge distribution before signal correction. However, it's now common to use a low input impedance voltage amplifier. So in fact, it's not measuring is not voltage but current. So it gets signal with the several overshot with the master corrected by the different with difficulty to distinguish the space charge. If not, the possible cause of overshot when it's for analyzer the sensor film and amplifier bandwidth. So it means this one we analyze this bandwidth. Another one is the analyzer for the produce the partial electrostatics deform. Now we can get the PEM method for planar sample. For the substance noise in the PEM method, so we can get the one just one sampling, one measurement is a very low the ratio noise ratio signal noise ratio, but after the 256 times average, so we can get the signal clear. If they get the more the times measurement average, the sample is the signal is more clear. So we proposed for this almost the standard for the so measuring processor by for the planar sample the data. From the orange one, this one we get the overshot here and overshot here. We cannot very clear is it the speed charge or the overshot. So if low impedance amplifier is used, so it's necessary go through the data processing flow. Otherwise, the signal overshot is mixed with the speed charge signal, so it's difficult to distinguish. So most research currently use the data processing this method, but some group perfect using the high impedance import amplifier. So it's not necessary using the data closing, but the average is also necessary. For if not, the noise is very too big. For the SIG sample, the where the high resolution is not required. For the SIG PVDF membrane, the high important impedance amplifier with low impedance is used. So some data necessary, maybe not necessary. So this one, first one, he gave the orange one, then change to the x to the from the time to the position. Then we get the data deconvolution. We get the clear this one. Then this one is deformed. So we need the transducer for the dissipation and attenuation curve. So we can get the similar this one. Then we get increase this one, so get the field. Then we can get the after calibration, we can get electrical field. The last step, we definition this one, we can get the speed charge distribution. This one. So sorry, this is in Chinese. This large is very similar than the thickness of the PVDF film. So, for example, for LDPE 0.5 millimeter with a 5 kilowatt, we can get the with applied voltage, then we can get the low field, so we get signal and without speed charge. After some time, we had the 15 kilowatt. After 30 minutes, we get the speed charge like this without applied voltage. So we know this one. You see the 3 peak, but the source peak maybe not real the interface charge. This one interface charge, this one the speed charge. This one we cannot see cannot say is a charge or not charge. I think the like noise here. So we get some comparison between the PWP and the PA. There is a bus have the two voltage circuit. It's the same applied voltage, DC voltage circuit. They're very different. There is for PA, there is a pulsed high voltage circuit, and for PWP is a pulsed signal voltage. The acoustic propagation is pulse is same. So the spatial resolution of the bus method is essentially the same in same order. The PEA method depends on the thickness of the sensor film, usually PVDF, the acoustic coupling, the pulse width of the applied voltage pulse, and amplifier bandwidth. The PEA method depends on the pulse of the laser or piezoelectric, and acoustic coupling and amplifier width. So the very similar is the purpose of acoustic pulse. But this one, PA is soft because the high voltage circuit is completely separate from the measurement unit. It can measurement unit in the very low potential. So whereas the PWP method is more dangerous because the high voltage circuit is separated from the measurement part only by the separating capacitor. So it's more dangerous just the operator and with high voltage just separated by the capacitor. The PA method constantly applied voltage pulse during the measurement. which maybe have some effect on the charge injection. Also, there are not very clear evidence on it. But we'll continue to comparison. This is the more difficult to control the sample temperature. There is a PEA method because we're using the measuring the acoustic using the sensor PVDF, or is also need the change temperature. The laser PRP is very easy, convenient for the has a few influence of factors, but the laser is expensive. But the sensor, the signal of a PEA is much less than the PRP method, so it makes it more difficult for the sick sample. The formula expression of PRP is very clear than the physical meaning of the PEA. The PEA is the function. The explanation is not very sincerely with the real charge, measurement charge. The bus method has takes the sun wave reflection, etc. The acoustic impedance matching will in the account is also anyway is very important. PRP method has a high sensor activity by than the PEA, so it's used for the single pulse measurement, whereas the PEA method requires the near thousands average of to improve the signal noise ratio. To measurement a very thin sample or very repeatedly charge of space charge, neither method is not suitable. Nothing is suitable. As a method of space charge measurement is not suitable for the quick performance to monitor the operating equipment. It means that we cannot measuring the space charge in cable in service. So we have proposed the 0.5 point method for the thermostatics. The laser pulse is reduced here, also using laser on the counting electrode on the surface of the thin film. As the sample absorbs the energy of laser due to the new form, the temperature change. For example, laser from this one is a temperature increased, but another side is cold. So the internal space charge underground the small difference. So also is the thermal extension temperature increase a little bit, so the charge a little more move. So it casts the change of the induced charge in the electrode, which generates a weak current extent. The electrical field distribution and spatial distribution inside of the sample can be obtained by analyzer. This method is proposed by Collin in 1973 when I was very young. He using the flash sample. In this age, the laser is not very popular in the laboratory. So he using the flash lamp was used for as a later pulse source. At this time, only the center of the gravity of the charge can the measurement due to the limitation of the computation power. Since 25, the measurement and the calculation of the electrical field inside of the thin film and the thickness of the several micrometer to 10 micrometer has been achieved by the using laser pulse by the thermal pulse as a thermal pulse source. So using the new calculation method and tools. So this one is an experiment setup for the TP method. So this one is a laser. For example, the laser diode is also infrared laser. The laser is about 25 nanosecond. The energy less small. For the PWP, the energy usually is 5 millijoule to 700 millijoule. But for this one is the energy much small. But average is not so much, the 100 times. He gets the sample from the two sides in some, then also the voltage applied There's also voltage applied on the sample. We using the amplifier. We get an oscilloscope. This is a typical signal. Be careful. This one in log. So the time is very long. The time spin of charge is very large, about 6 octaves range. So, the bandwidth of amplifier or system is very wide. So it needs high demand of the amplifier. It's not very easy for the very large bandwidth amplifier. Even it's not very high frequency. So this is a data processing method for the TP. The sample using the thermal pulse, we measuring current. We using FFT get the frequency spectrum. Then after deconvolution, we get the field equation. By the Poisson's equation, we get a charge distribution. You can find that this equation is very similar with the PWP. It's a change, something change. The displacement, the P with the T, temperature. But the temperature is not wave. So temperature is something like reduced, something like that, not a propagation. So so it's not easy to resolve this one, the integration equation. So this need to consider the alpha epsilon and alpha x is a factor of the permittivity for temperature and cosine for linear expander. So it's not easy to get a solution integrations, and it's also very sensitive for the signal noise ratio. Sorry, ratio is not P. Mistake. Oh, this one is a method for equation. We need the some parameters for this equation. We use the different. We try the different calculations method. We can get the different result. Some result with a more high the resolution, the ST method. Usually, many people using the Chekhov method, but this one is also can be used. So these are some measurement result for the under the low applied voltage. For example, the 780 voltage for the 30 micrometer. This one is 130 volt for the 1.3 micrometer. So the field is also very high, but the sample is very thin. So we can get the good resolution near sample about 0.00205 micrometer. But it cannot use it very thick. The over 20 micrometer is almost not possible. So the main characteristics of TP method is because the thermal diffusion is sensitivity for the slow and then the acoustic wave velocity. So the spatial resolution of the thermal pulse method is higher than that of the PEA and the PWP, and the current reach about 0.5 micrometer. Because the thermal diffusion is not the form of the wave, the spatial resolution of the thermal pulse is scientifically than the uniform, less uniform in the long direction, and cannot use by the thick sample over than the 20 micrometers. Also, because the thermal diffusion is not a form of wave, the measurement result of the thermal diffusion is very unintuitive and must be subjected to the complexity convolution operators to the measurement for and results obtained closely related to the deconvolution operator. Therefore, there is a relative use TP up to now. For these methods, no matter the space charge, which space charge measurement, it's important to have the both high spatial resolution and large spatial measurement range. Scientifically, for the thick is not possible. In principle, it's a difficulty to have the proposed cement measurement with a resolution higher than 1 or 2%. or the total measurement. For example, your sample is thick, your resolution should be low. This is a limitation of the measurement principle. So we come quickly. Then we give the second topics is about the insensitivity in space charge measurement. We get similar some the experiment phenomena. Planar PE with the PEA, with the EVA plus the carbon black semiconductor electrode and the DC high voltage measurement sends the evolution of space charge. Then the surface fluorination for the PE and surface fluorination for the PA electrode. For the uniform planar PA sample measuring space charge at a different position, we can get some experimental phenomena. We can get this one. We try the original sample is something like that, many space charge. If the fluorination on the sample is more or less, but we relation on the fluorination on the electrode, he have much more space charge than the no fluorination. This one is the first one. Then we get the possible, the why. We need to understand why. The homo charge or hetero charge injection from the meantime for the space charge, but it's not in same position. It means that the space charge is mixed the positive charge and negative charge, but we're measuring the resolution is not very high. So space charge measurement is a result is average. It means to help understand the famous result of the Professor Montanani, the fast moving charge pocket. The positive and negative meet together, but no composition. As they are not in some position, it means that he don't meet. The action of the space charge fluorination is not to block charge, not to block charge injection, but restrains the definition impurity from the EVA and the C plus carbon mixed carbon black, not CB electrode. The space charge fluorination of the EVA carbon black charge can restrain the definition of the impurity from the EVA plus carbon, sorry, CB, but no affect the conductor the carbon practice. There are where it's not change the injection from the homo charge, but reduce the hetero charge. So the charge injection increases. For the planar sample, space charge is not uniform in two-dimensional. So, but activity measurement is not consider the charge distribution in the planar dimension. We measure only this side, but don't consider another dimension. So we give some experiment. For the unit plant polyethylene sample, measurement space charge in the different position, we get the coordinate per step 1 millimeter. We're measuring this one and this one. The measuring spot as shows the gray and the propagation result is in yellow. So we measure this one, but too much results, so we show just this one. So we get has a different the space charge. So see, the hair is also different. The signal is a different position without a space charge injection. As the thickness of the sample and the electrode are not uniform, the signal is not exactly same, but they are from are same. The form same. The electrical field thickness is more important. So we can get the after apply voltage. So we can find the hair is different. The after the charge injection, the measurement in the different position and correct result, we move a little bit on here, remove the effect of electrical thickness. So measuring result and sensitive to the measuring position, it means the result is not mean uniform, average. So we measuring the laser. The typical laser spot is not uniform. This one is not our laser, is typical by the manufacturer. So even this one is a laser is not uniform, something like this one. For our laser is a more this ideal spot, the Gauss effection. So our laser is more not ununiform. So hence the measurement results not uniform, not the average of a measurement error. So we get the simulation. For the spatial injection, accumulation and deform, it should be in the DC voltage, even the electrical field is uniform. The spatial charge is not uniform. During the charge injection, the homo charge and hetero charge exactly simultaneously. So there is a spatial charge, including sometimes the homo charge and the hetero charge means positive or negative. The homo charge and the hetero charge is not the same spatial position, so it cannot recombine quickly. In the case of planar sample, the spatial charge injection is not in same layer, so it's not both. They are both positive and negative charge. So for the measurement of spatial charge diffusion, it should be either way, no any method. The measurement at the one-way distribution in the depth direction. It assume the charge injection, the charge is uniform over the measurement error. This is a condition. The measurement error is not small, and the error scale is usually larger than the medium thickness scale. For LEAP, for example, the laser therapy, the laser is not uniform. For the PEA method, the sensitivity of the piezoelectric film, neither PEA and the PVDF, is also not uniform. The measured spatial distribution is the apparent or the epigenetic integrated measurement result. The following slide is an emulation of the spatial charge measurement, not real measure charge potential. This one. If measuring this side, we found the spatial charge something like that. Read the spatial charge, then the measuring, we get the signal like that. Then if the position B, we maybe get this one. Is a different form. See here, this one is a current. This one C is a more different current. So this is intensity of the laser. This is partial. So we can get the C is like this one. So we in the different position, it's possible for get the different result of the spatial charge. Yeah. So for clear understanding, the difference among the measurement current is intensity exactly. So we cannot. It's not the measurement, but for understand this one. So for PEA is also possible. We not measure, but we get some reference. So we get his distribution in the wafer position. He gets a different PVD sensibility. How to understand above experiment? Even for a planar sample, the space charge may be not uniform distribution in any planar. The space charge distribution is not uniform in 2 dimensions. The result of laser is not uniform in measurement spot, and the measuring result is not sample average result. The piezoelectricity of PEA and PVDF are similar, is not uniform. So PEA method is similar with PRP method. It's very difficult to measure the energy distribution for laser, spot, and the piezoelectricity of the PVDF and the PZT. So it's not possible to the calibrator for each measurement. So measuring space charge in the apparency, epigenetic integrated measurement. So about the small conclusion, the insensitivity of the space charge measurement is clear. So small measurement position shift may be induced by bigger difference of the measurement. You move little, maybe big difference. For the electrical equipment like the cable, they are not a typical position, so it's not variable to the monitor for running insulation. The space charge measurement in the short time or and not in the inside for a few sample is not variable for to pay attention and analyze. So gives us some noted insulation issue and suggestion. Not believe your direct measurement result too much. It's recommended to separate the test to minimum the random error or a double check for any important result. The measurement of space charge evolution should be performed strictly at the same position. It's important. For the combination of space charge distribution between the different samples, it's recommended to separate to repeat the result to get the average or compare their average trade. So you cannot measure it one by one. It needs average. Then we have time or no time, the Yuan?
I think we are running out of time, and maybe we can leave some time for the audience to ask questions.
So we give quickly the I have new result for the combination. We combine the sample. So we develop the probe, active probe for the measuring the space charge by the piezo and using the compens. This one is a probe. This is a probe for the space charge measurement. So the result is very similar than laser. The combination is similar. The new system can use the measuring space charge distribution inside. Also, by combining with the traditional piezo, PWP or laser, the new system has the very similar separated insulation. So this one have the American Panda in this year. So in near future, what's important? Just one page. Understand clear why is the important space charge the role in the DC high voltage, maybe not only for modification in the electrical field. To be clear, if if it is important for the DC capacitor or the space charge in thin film, there is need many things to do. Then to develop the technical for measuring space charge with a high resolution, and to develop the technical for the space charge under the high frequency. It's also possible to have the electrics have the working high temperature. It's very difficult also. This anyone is very difficult. So thank you for the attention. We have more for space charge long for real cable, but we scan it. No time. Oh, now we maybe the time for discussion. Yuan?
Okay, thank you, Professor Zhang. Thank you so much for your fascinating presentation. I think maybe we have several minutes for audience to ask your questions, and you can just type your questions in the chat box, and I will read it for Professor Zhang. Okay, I see now about 40 audience is.
Do you need my screen again? Not I close the share.
Okay, we would. It depends. You can share your screen now, and I think maybe we
okay,
can.
If somebody say the page, I don't know maybe.
Now there is no.
Yeah. Okay.
No questions now, but I think if you have questions, you can type in the chat box.
Yeah, I can see it.
Yeah.
No?
Is it? A question comes up. Is it possible to find the space charge in a dirty medium? It's a name.
Yeah. What?
Yeah, he asks. Yeah, I think it's Tanzila. He asks, is it possible? Is it possible to find the space charge in a dirty medium?
What's meaning in dirty medium?
Maybe not clear. Can you? Yeah.
Dirty medium. Dirty medium means the polymer mix the some very much the impurity, right? I understand.
Maybe some fillers.
Of course,
Yeah.
the measurement space charge in I don't know what means the dirty medium for the measurement the space charge in the with the many interface. For example, dirty is depends your dimension of the particular. If a particular very small than the acoustic wave, so it's the same. If the particular dimension of a particle is much bigger, so it's a very big scanning for the acoustic, it should be very difficult. I don't know. I understand your question or not.
Okay, maybe I think Professor Zhang has answered it very clearly. Yeah, it's all right. Okay, audience, you can just type them publicly, not necessary to privately to test it to me. And the second question comes: how long should one keep a sample under the space charge test to get the right and sufficient information? How long
Good.
should we keep?
This is a good question. It's also very difficult question because in any laboratory, the people don't like the trace very long time. But space charge for the, as my experience, the space charge in the PE, polyethylene, polypropylene, not not PMMA, not include PMMA, is never stop. So even the applied voltage over some weeks is also still change. So it also depends the temperature. The space charge is depends the correlation and motivation. This is a very good question. Industrially, we cannot use it, test the monitor space charge evolution very long time. So in laboratory over some days is also enough long, but this one doesn't mean the space charge is stable. So its question is a very good question, but it's very difficult to answer this question.
Okay, I think we don't have much time to have. We will have one one last question. A Chinese researcher Qi Tianren, he asks, what's the minimum spatial resolution of LIPP, and how can get to the minimum spatial resolution?
For resolution or LPP, it depends the partial width. If using the laser, for example, for cable is using the nanosecond laser. It means that the width is the same nanosecond, so it's very easy to use. But the resolution is about the 10 or 20 micrometer. It's not very high, but for the film is not useful. For example, for the PI or the PP film is needed a picosecond.
Hello, Professor Zhang. Oh. Hi, Professor Zhang. Can you hear me?
Thank you for what?
Oh,
Stop.
because you just have some minutes offline, maybe. Okay.
Okay, we did discussion for another time, or maybe send me later. I have email. Yeah.
Yeah, yes, you can share your email on, I think maybe on the screen, because
Yeah, you can screen or the yeah, it's a very good question for the resolution and the time. The first question I'm not very understand very well. Maybe I don't know the answer is clear or not. Okay.
Okay, so I think there are many famous professors also online. They have heard all the entire webinar. And thank you again. Thank you for Professor Zhang, and thank you for all the audience.
Okay, you're welcome. Thank you for your listening and thank you for your attention.
Okay.
Okay,
Thank you.
I close. Okay.
Okay.
Okay, bye.
The webinar
Bye.
is
Good night.
Good
Good night for me. Good morning for everyone. Okay, bye.
okay. Bye.
Bye.